Okay, in this video I would like to give you an example, a worked example of something that we can call conditional distribution. It'll be quite cute, I think. The way it works is like this. I hope you know by now something that's called exponential distribution. That is a distribution that x value can go from 0 to infinite, and the function, the PDF of it is e to the negative x. This is one of the famous distributions when you start learning about continuous distributions. So we'll do something here interesting. We'll take a random number that is in this distribution. So it can be any number from 0 to infinite. And obviously, if you know that something about this distribution is that it tapers down. By 0, it's the f of x is 1, then it gets smaller and smaller. It's e to the negative x. The higher x is, the lower the curve is. So you should know by now that the higher the number is, the less probability is to get that exact number. By the way, I'm just trying to go over something. When we say what's the probability to get 7, so the answer is e to the negative 7. We all know it's impossible to get exactly a 7 because it's a point, it's a line, and nothing can be exactly on the line. The best way to understand it for the human brain, the way I understand it, and I think that's the easiest way to grasp it and to have a concrete. It's very important in math you have your concrete picture in your head. The concrete way of understanding is like this. Let's use 0.01 as a small number, right? It's 0.01 is quite small. It's 100. So we can say, make this statement. The statement will be quite accurate, that the probability that this thing should fall between 7 and 7.01 is e to the negative 7 times 0.01. That is that thin rectangle. So if you're asking, for example, the probability that this should survive between 7 years and 7.01 years, which is exactly in that area, it should survive, then that will be 7. That will be e to the negative 7 times 0.01. If you have a calculator, that is a number, exact percent. It's a tiny number. That's the probability that this object should survive between 7 and 7.01 years. It's the best way to understand it. You can rack your brain, you can think about all kinds of philosophical, but the simplest and the most practical way is anything you take between 7 and a tiny region next to 7, we call it 0.01, will be 0.01 times the f of the x of 7, that is e to the negative 7. Okay, this is just a side note, just for people who have a hard time, just like me, understanding what continuous distribution is all about. We should return now to the main subject. So now we are discussing, there's here a guy that wants to do a very interesting thing. He's doing like this. He is, first of all, using this special random generator, something that can give him a number from 0 to infinite, using the probability of e to the negative x. Let's assume he has such kind of machine. I used to imagine the way to do it properly would be, imagine you have on a paper a curve from e to negative x from 0 to infinite, and again, you throw a tiny dot of dust on this paper, it can land anywhere. So obviously, if it lands on the where the x-axis is 3 or 4, it's a higher probability than it should land where it's 70 or 80 or 90, because the curve goes down. So you can imagine it that way. Basically, you're doing this probability of this random variable that can go from 0 to infinite with a PDF of e to the negative x. Now, once you did this experiment, so again, it can be, the x value can be a half, a third, a quarter, 2, 3, 4, 5, 8, 9, 90, it can be any number from 0 to infinite. You take that number and listen to this one. Listen to this one. Here it gets a little quite complicated. If it lands from 0 to 1, that tiny section of the chart, of the graph from 0 to 1, then you take that fraction, and that's how you program your coin that you're planning to toss now to see if it will be heads or tails. That coin will be programmed that it should have a bias to heads according to what x was. So example, if it fell on x 3/4, then this coin will have a probability of 3/4 of to be heads. If it fell on the point where it's a third, then the coin will have a bias towards a third. It's an imaginary thing. Imagine that you can somehow program that coin to have that kind of bias. We know what coin is 50-50, heads or tails, but imagine you can put in the head of the coin. You should be biased a third toward heads. You can use it. It's not so hard to imagine. Let me just show you a graph. That's kind of what I'm talking about here. As you see, this is the typical e to the negative x, and here it's 1. Now, as you see, there is a point there. That point is where x is a third. So if that falls on that point of the graph, it means that the coin will be biased towards a third. Now again, I'll repeat. There's no probability it should fall exactly by a third. However, we are telling you if it's not exactly by a third, so it's by a tiny after a third, so then the coin is biased even more towards heads. So there is always something that the question obviously will be, I just want to finish the question, what is the total probability the coin should be heads? It's dependent on a two-step process. First, you throw this tiny, you shoot an arrow on this huge graph, and if it lands before 1, then we bias the coin towards that point of x. So when x is a third, the coin gets biased a third. If x is 7/8, here you see I made an x there. That is a point where x is 7/8. So this is, it's by the way quite a high probability, because we know that in this graph, if you learned some probability, know that most of it is before 1. Most of the probability in this curve is, in fact, to be exact, we know that there's only we know that in fact there is only a chance of 1 over e. I'll calculate it. 1 over e, that is 1 over e. Oh my god. 1 divided by shift e to the negative 1. Let me just do e to the negative 1. E to the negative 1 is 0.3. It's only 36% chance it should be after this line. So anyway, it's just a side note. We must realize that this is a very tiny chance that this should actually happen, that it should be after this line. Most of it, it's 64% that it should be before the 1. So anyway, he threw that dart, as we said, and it lands on somewhere on this chart. And let's assume it lands on the 0.78. So that now you automatically have a coin ready in front of you that you program it. There should be 7/8 heads. How about if the dart lands here? By 5. You see, I wrote there 5, and there's a dot there, but where it says 5. So, what is if it lands by that point where it says 5? It makes no sense to program a coin with 5. Then we'll program it with reciprocal, 1 over 5. That's our way to work around this problem. If it lands on 8, it will be biased 1 over 8. So actually, as it goes further and further, it gets less and less towards the, if it's 100, heads is only 1 over 100 chance. But actually, since it's higher, so there's less of a chance it should get to that point of 100. So whatever it is, it doesn't seem that we're going too bad here with figuring out what will be the total probability of heads. So again, I'll ask the question again. We're using this interesting experiment or game, whatever you want to call it. The game works like this. First of all, you have this huge paper, endless, infinite paper. It goes from 0 to infinite, and it has a PDF of 1 over of e to the negative x. You throw a dart. It can land random in any place of this whole infinite sheet of paper. If it lands anywhere before x is 1, then we just take that as the indicator. That will become the probability of the coin should be heads. If it lands after that, then we take the reciprocal of that. For example, if it lands on 5, then it will be a fifth. So I want to show you how I did it. I think it's a good way. We'll divide into 2 parts. First we'll take the first part, So the probability that it lands before 1, we know, is 1 minus e over 1. So you take that, and in this context you would figure out what is the, so I'll show you how to do it. I'll do it for you on a piece of paper here. Okay, 1 minus e negative 1, that is the probability that it should be one minus e negative 1, that is the probability that it should be on the side that's less than 1. That's on the screen, is on the left side. So if that happens, then what is the probability that it should be heads? You integrate x times e negative x dx from 1 to 0. What am I doing here? I'm taking each tiny rectangle that is the size of e negative x dx, that's like a tiny number, that's the probability that the number should be x. For example, if x is a third, it's a third times e negative a third times a tiny number. That is, we do that all the way from 0 to 1, because that is all the ways it can be heads. If x is a quarter, so it gets a quarter times e negative a quarter. And actually then it's a little bit bigger. The e negative a quarter is bigger than e negative a third. But then again, you have a lesser of a chance, only a quarter of a chance it should be heads. So that's calculating together the total probability of heads. Because we're taking here, first of all the probabilities of getting the number, the first toss into a quarter, that's e negative x dx, and you're multiplying that by a quarter, because if that happens, there's only a quarter of a chance it should be heads. You add together all these products, that's the integral. That is the total probability of getting this if it's less than 1, I'm sorry, I have to erase this little mistake that I did here. Okay, I'm sorry. This is nonsense what I did. This is the main thing here what I'm showing. Just take all these rectangles. That is the probability. It should be the first dart should be, for example, should fall on a third. It's e negative a third times the x, and then if that happens, there's a third of a chance that it should be heads. You do this from 1 to 0. However, this only considers the cases where it falls from 1 to 0. What happens if the dart goes from 1 to infinite? That is on this video on the right side of the screen after 1. What do we need to do then? The answer for this is, let's see, we'll write down on a new formula that will take care of this problem. Look at the right side, plus from infinite to 1, that goes all the way the right side till 1, 1 over x, e negative x dx. Why is that? Because right now we are saying if it lands on 5 or 6 or 7, so let's say it should land on 5 is a probability of e negative 5 times dx times a tiny number. This, if that happens, then there is a probability of 1 over x at a fifth. That should be heads. And so on. But basically, if we add together these two integrals, we shall get the right answer. And I just need to add these two integrals. How do we find the integral of the first one and the second one? So we can look it up in books and charts. There's in the computer programs where you can look it up. I would continue in the next video. I'll give you the answers as it says in the books. And also the next video I would also tell you how to get a different way how to do it. Same thing what we did right now. Thank you for listening.